Okay, this is a short video segment on uh, quasi-static analysis, or what is known as transient static analysis, in order to model a creep problem using a four-term Prony series model in the 3D Experiences FEA module release 2022x. Let me remind you that the FEA module in 3D Experience is actually the stripped down version of the Abacus CAE program or Abacus standard program. Now, if you are an Abacus user, you are probably familiar with some of the features and the icons that will come up in the 3D Experiences FEA interface. However, it should not be taken for granted that anybody who can do the Abacus CAE can actually, without too many difficulties, run the same problem on the 3D experience. It does take some effort, and the purpose of these videos is precisely to prepare either the novice users or uh, uh, experienced Abacus CAE users to be able to tap into the FEA module of the 3D experience. The problem that I'm going to do is a creep analysis. And if you look at the interface of the 3D experience, you see for the steps, the procedures, you see these different types. Okay, the specific one that we want to do is the quasi-static step. Okay, I already have one video using a Maxwell model for a creep analysis using a quasi-static approach. But this is a more complicated problem because it uses a four-term Prony series as opposed to one-term Prony series. Okay, so here is some documentation on the quasi-static problem in 3D experience. Basically, if you have a problem which has time-dependent material properties, but the inertial effects can be neglected, low acceleration or very low mass, basically, you can use quasi-static icon and the procedure in 3D experience. Okay, mind you that any problem can be solved with Abacus explicit or the explicit version of the program if you have license to it into the experience. However, it is unnecessary to solve simple problems, and one can, for example, use the quasi-statics approach in 3D experience to do that. Now, the reference that I'm using to compare my results with is this YouTube channel. It's pretty good presentation, but it does it with the Abacus CAE, and it does also implicit dynamic integration. It's not doing it as a quasi-static problem. So we have basically an epoxy sheet like that with the dimensions given, and one end of it is clamped and the other end is subjected to a constant pressure of 100 or 10 megapascal. And what we want to know is what is the displacement and the strain after 1 hour of at the right or left end point of this sample. The properties are given in this paper or in this video tutorial or here, Young's modulus, and there's a density given and Poisson ratio. Now we don't need this density because we're not solving as a dynamic problem, but in that tutorial, in that video, it's actually needed. Okay, uh, that information, since we're using four-term Prony series, you need to have the data, and the data beyond what you see here is coming from a paper which is listed here, and basically you need four-term Prony series, meaning you need four sets of 4 rows. Now the middle one, the K's are not necessary in our problem. All we need are the GI values and the tau I values, and these tau I are the relaxation times, okay? So anyway, this is the data that's going to be inputted in 3D experience. The fellow in this video tutorial is actually using a plane stress model, a plane stress parabolic element with this kind of a density, and comes up with a prediction of strain as a function of time after 1 hour and displacement as a function of time after 1 hour of the left end of the bar generated or given by these two graphs. We're going to be comparing our results with this. Now, in my case, I'm going to be using, in 3D experience, you don't have a plane stress or plane strain modeling capability. So I will use a shell element, parabolic shell element with a thickness of 1 millimeter, which effectively emulates the plane stress condition. Now, the mesh that I'm going to be taking is fairly coarse, and it's only 5 elements. And it was shown here, shown on the top, as you can see. And the data that I mentioned to you, those G, K, and tau are going to go in the table like that. And just don't forget to activate this time radio button, otherwise it's not going to work. Well, I'll lead you through the steps in a minute. And also, because we're doing it as a quasi-static problem, these are the 1 hour is 3600 seconds, and these are the values I'm going to be using. This number, maximum creep strain rate increment, is, at least our problem is very insensitive to this. So you can use 0 because 0 will give you an error message by the software, but I will use 1, but I've tried other values, same thing. Also, I've deactivated the geometric nonlinearity effect. That's not needed. Okay, so let's go ahead and create our surface, because it's going to be messed with shell elements. I mean the generative shape design, because I'm going to create a surface. So on that vertical plane, I will sketch a rectangle which is 100 millimeter long, and the width of it is 10 millimeters. Exit. And we're going to fill this thing with a surface. So we go to surface, there is the fill option, FILL option, say OK. So notice that the surface is placed on that rectangle. Okay, that's pretty much it. Let's go and create our material. So we go to Tool, Create a Material. I'm going to call this thing 4term Prony series. Okay. All right. So this is just a placeholder. Right click, apply. There's no data in it yet. So on that part, use the green check mark to make it go through. And now we expand the tree and we can input our values here. So we go to material, this branch, material, structural. Now density is going to be put in this box, but we're not specifying the density. So I'm going to go to the next row, abacus multiphysics, mechanical elasticity, elastic, and that number that I had was 4060.1 MPa. That was my Young's modulus, and Poisson ratio 0.37. Incidentally, This problem is also fairly insensitive to Poisson ratio. You can try it. Even 0 will give you pretty much identical results. But anyway, we use the same data. Oh, one other thing. Do not forget, because you're dealing with a viscoelastic model, this instantaneous radio button should be checked, not long-term, instantaneous, because these values, Young's modulus, etc., change as a function of time with time. Okay, Young's modulus, shear modulus changes as a function of time. Okay, so that's good. And then we're going to go to viscoelasticity and viscoelasticity. On the viscoelastic, you select it, and don't forget to select this radio button, time. Now notice that this table pops up, which allows you to input stuff like this, okay, G, K, and tau. So let me input my numbers in there. So that one is, or you can import it as an Excel series if you want, but I will type it in 0.0738. And it doesn't round it off, but because of the display that I have is only three digits after the decimal point, it records it like that. But the value is 0.0738 that I inputted. Then this guy is 0. And for tau, we have 436.4. Okay. We go to the next one, 0.147 K0, and tau is 0.06407. Next row is going to be 0.3134, your K is 0, and your tau value is 0.301163. And here is the last one is 0.3786. The K value is 0. And over here I have 7.321 e to the minus 7. Okay, so remember, if this thing is bothering you, you can just change the display of the figures or notation, numerical format, so that you have more digits, so that it doesn't round up like that. It actually not rounded off; it displays it differently. And that's pretty much it. We say okay. Let me also save my work. All right. So now we're going to go to and mesh this thing. So we go to the structural model. Oops. We go to structural model creation. And because I'm using shell elements, I don't have any solid objects. So I'm not going to use that. I'm going to use empty FEM. Okay. So I notice that nodes and elements are not created because I don't have a solid element here. I have to do that myself. So you go to mesh and use a surface quad mesh, that face, and the value that I'm using for mesh size is 1 centimeter or 10 millimeter. 10 millimeter. If you look at it, this is what I had, 10 millimeter. Okay, it'll give you mesh like that, and yeah, that's pretty much it. And parabolic, right? So mesh. Or, okay. Now, if you want to see the mesh, you just update. See that right there. There's the update. If you just had pressed mesh, it would have shown it. We also have to do the thickness, shell thickness. So we go to properties. This is a shell section, and select it from the 3-part body right there, and put 1 millimeter thickness for the shell. Yeah, that's pretty much it. That creates the basically finite element model. And now we're going to go to the shell scenario creation. where you apply the loads and interface and say what kind of analysis you want to do, etc. So first of all, under finite element model, you go to the model that's just created. All right. And you go to procedures tab, and there's the quasi-static analysis. You select it. So this is over 3600 seconds, over 1 hour period. Yeah, 1 hour. And the maximum number of increment, I think I suggested 10,000, so that you just don't run out of it. I mean, it's not going to, it's probably going to be 100, but 100 is going to be good enough depending on what you put down here. But I just, to be on the safe side, I just made it big enough so that it doesn't abort because it runs out of, number of increments, okay? And these are the things that I'm going to be using. So for starting point, I'm going to use 0.01. I just want to tell you that these type of problems are fairly insensitive to the size of this thing. So as long as you put something reasonable, it'll work. Even 1 second probably will work, okay? And then over here, I think I said maximum time increment of 100 seconds. Yeah, that's fine. Now, as far as the maximum creep strain, if you leave it at 0, it's going to bomb out. It's going to come back and say can't be 0, etc. So it's fairly insensitive to this. I have put a 1, but if you even if you put smaller number, it's going to work too. But anyway, so you may want to experiment with these. It makes no difference in this particular problem. So I don't want to include the geometric nonlinearity. Uncheck that. We say OK. And let me save this. All right. Why don't we go ahead and apply our loads and restraints. Yeah. So you go to load. This end is clamped. The problem is that when you select it and you say, well, wait a minute, not load, I'm sorry. This end is clamped, so you go on the restraint. When you select it, when you say clamp, you see it disappears. That's because you're basically picking that sketch. You don't want to pick the sketch. Let me hide the sketch here. Now I can select this left edge. You see, it clamps it right there. But before, when the sketch was showing up, the sketch was that entire rectangle and it caused a problem. So I just hit the sketch and selected that. Okay. Now on this side, we have the load. The load is shell edge load on that face, on that edge. Now, we have the pressure. If you multiply it by the thickness is 1 millimeter. So that 10 MPa times 0.001, which is 1 millimeter, will give you the thickness. Will give you the load there, edge load in units of Newton per meter. Okay, so that will be, if you do that, negative 1, 2, 3, 4. Yeah, the unit automatically is going to become kilogram per, or it's weird, second squared, but anyway, it is actually Newton per meter, which is equivalent to that. And we say, I just want to make sure that, yeah, okay, 10,000. Where is that? 10 MPa multiplied by that thickness is going to give me that. This is 10 to the 7 multiplied by 1 millimeter is going to be 10 to the 4. Yeah. Okay, very good. Now, we're pretty much done here. We go to simulate. Let me ask for some data here. For example, you can ask for additional data, stresses, components, and strains, again components. Okay, you can have the whole model, or this is a very simple problem, or the stuff only on that edge. Really doesn't matter. I'll say the whole model, and every every increment. This you know, if you have a gigantic model at every increment, a lot of nodes, then that could be problematic. But it's a very simple problem, so every increment will be fine. Okay, that's pretty much it. We're gonna run it, save, and then run. Okay, so first of all, model check, always a good idea. So that if there are any obvious errors, they're gonna may be able to catch it here. And then the simulation check, any obvious errors are gonna may pop up here. I'm pretty sure this is okay. It's a very simple problem. I want to remind you that we are doing this thing as a quasi-static problem. In that video tutorial that I'm going to be comparing it with, it's done as a implicit dynamics. It could also have been done as explicit dynamics, but it's unnecessary for this problem. In 3D Experience, at least version that I have access to, 2022x, the default access is to implicit dynamics, not explicit dynamics. I'm sure if you had the proper role, you can also do that explicit dynamics, but I don't have that role assigned to me. Okay, so simulation checks okay, and now we're going to run this thing. It's going to be very fast. I also ran this problem with implicit dynamics and you got identical results. But I'll just leave it the way it is. Quasi-static. Okay, if you click on the iteration, you can see that it's going very fast, and we are already reaching, we already did reach 3600 seconds. If you take a big time step, then the curve that you generate are going to be not as smooth as you may desire, but that's okay. All right, so here's the situation. Let me close this there. So this is the initial step right there, initial time 0. But if you, and you're looking at von Mises stress, so if you go to other steps, of course, the von Mises stress is not going to change, okay? The stress is going to be that 10 megapascal. It's not going to change here. But the displacements will do. So if you look at it here, you put the cursor on it, you see that it's 10 megapascal. You can see that over here, because of the clamp, of course, there is some stress concentration and things like this. Now, when you look at the displacement, you get 2.56 millimeter at the left end. Now this is fine. There's no problem. Of course, if you start at the way at the beginning, the value is going to be smaller. You can see that when you start initially, see that the displacement are smaller and smaller, and gradually builds up to that after 1 hour, 2.56 seconds. Okay, but I want to be able to compare my results with this fellow's work. So let's go ahead and plot the strain as a function of time and velocity and displacement as a function of time. I should be getting these graphs, and I do. So the way to do it is you go to plots, plot from field, So, for example, translation of this point, select this point. This is node, I think it's node number 1, looks like some node here. And then translation, for example, in the direction Y, not the magnitude, sorry, direction Y is direction 2. And just say apply. And there we are. See, it's negative because it's moving to the left, it's negative value. And that can be compared with this fellow's graph. Okay, it's pretty much the same. Okay, so that's this, and let me close that. We can also generate something else, namely strain. Strain, so not translation, but strain E. The component is component E22, and apply. There we are. This strain, you'll notice that it goes to roughly 0.02 something, can be compared with that fellow. Okay, they're pretty much in agreement. That's pretty much it. So I've done 2 problems on 2 videos on quasi-static analysis when it comes to creep. In one case, there was a Maxwell model, a single term of the Prony series, just 1 term. Here we did 4 terms of the Prony series, and yeah, looks good. Good luck.